Can everyone see okay? Actually, I didn't realize how shallow this room was. If you can't see something, just shout and I'll say it again or write it bigger. So it's my pleasure to give this talk today in front of all of you, and also because I get to use these blackboards that I've been looking at for the past few years and I never got to give a talk on. And also because I get to talk about these derived Hecke operators, which are the main topic of or the main characters in my PhD thesis, and I'm quite fond of them, so I like to talk about them in front of everyone. So my plan is to actually focus on these last two words for most of the talk, Hecke operators. So these are going to be certain operators on certain complex vector spaces. They come from number theory, and the vectors in these vector spaces will be called modular forms. So you'll see this word again and again and again. After I talk about a bit of this classical theory, and then move on to what Hecke operators are on these vector spaces, I want to talk about how to use sort of mid-20th century algebraic geometry to reinterpret these complex vector spaces as the complexification of some abelian groups. So sort of working over the integers, or working over a general field or ring. And then I'll start quoting some theorems that say that you can not only do this over a general ring, but actually over a general derived ring. I'll mention what that is when the time comes. It's nothing to be worried about. And then I want to not construct the derived Hecke operators, even though I think the construction is super nice and cool and it's a nice story in and of itself. Come see me if you want to talk about it. I just want to give you some tricks you can play with these derived Hecke operators. So there are some very naive things you can do with these, some very small calculations in homotopy theory which produce some little baby congruences in number theory. And I just want to show them to you because I think they're neat. Okay, so let's get started. So let's start talking about modular forms. So first, let's talk about complex elliptic curves. So a complex elliptic curve is this space. So it's a complex numbers modulo some lattice. So what is lattice? A lattice is a choice of real basis for the complex numbers. So it's an R basis for C, and we usually write it like this. It's generated by some omega 1 and omega 2. Okay? And just to give you a picture of what it looks like, I mean, a picture up here, usually have a complex plane, something like this. Maybe you have your omega 1 here and your omega 2 here. And then, of course, you have your lattice that looks like this. There's one vector, there's our second vector. Yeah. And our lattice starts to look like this. Okay? And the fundamental domain of our elliptic curve, oh no, did someone realize a mistake? No, it seems fine. The fundamental domain of the elliptic curve defined by this lattice is going to be this little parallelogram here. So usually when we think about complex elliptic curves, we think about this little parallelogram. So another little definition is when we want to call two elliptic curves the same.
What color is it?
I think I will definitely use colors. Oh. So this is what a complex elliptic curve is. And I want to say that we write C modulo a lattice is equivalent to another C modulo, the same C modulo a different lattice, if and only if the lattices differ by some complex unit. Okay, so
I do not understand when you say that it's a basis.
Yeah,
Maybe the Z-span, integer span of omega 1 and 2.
oh yeah, you're right. Yeah,
Yes.
that's what we think of these guys as.
and that's how you have to read the next line.
This one?
Yeah,
Or this one?
yeah. So the lambda. So
Oh,
it's not for the basis; it's for the lattice.
yes, that's true. That's true. So this is as lattices. Makes sense. Yeah, you're totally right. Okay, so let me make a few observations about what I've written here. The first one is that this equivalence relation between these complex elliptic curves given by these lattices means we can sort of normalize things. So first I want to mention that omega 1 divided by omega 2 or the other guy, omega 2 divided by omega 1, lie in what I'll write as H, which is this complex half plane. And that is simply because, well, if these guys didn't lie, oh, sorry, the imaginary part of Z has a condition, it's greater than 0. You could imagine that perhaps this quotient lands on the real line, but of course this would mean that these two guys are not an R basis of C. They would be, well, yeah, they would be linearly dependent. Okay? So in other words, oh yeah, and then here's the other thing, is that we can normalize C modulo a lattice like this. As follows, yeah, this is the point you were making. This is the abelian group generated by these two elements, not the span of these two guys. Yeah, that's a good point. Does that make sense to everyone? Okay, good. Language confuses me a lot. So what we can do is we can let's just assume that W1 divided by W2, it lies in the half plane. So we can then just move this W2 to the other side, and we end up with something like this. So in other words, we're kind of using, we're being a little bit too general by allowing two variables, W1 and W2. We could really just ask for one variable like this and ask it to live in the complex half plane. And that'll give you a representative for every isomorphism class of these complex elliptic curves. But there is still a little bit of redundancy. So if we have two things, so a tau and a tau prime living in the complex half plane, I'll save my omegas for complex numbers and my taus for half plane membership. If we have two guys living in the complex half plane, then this elliptic curve, defined by the first guy, is equivalent to the elliptic curve defined by the second guy, if and only if. And so these first two parts, basically I prove them by saying it out loud. The second part is like a pseudo exercise.
So why is it called elliptic?
This is a really good question.
Is there something elliptic inside?
Yes, definitely.
Why is it called a
These are all good questions. So I'll answer the second one. It's a curve over the complex numbers. It looks like a surface, but of course that's a curve over the complex numbers. It's like a plane. For the second question, no, that sounds very patronizing. It's really, well, it's a long story, really, that goes back to Gauss and Weierstrass and stuff like this.
Both our master students take a course on that, just to learn the answer to that question.
Oh.
Yeah, like there's very interesting transformations between sort of elliptic curves from algebraic geometry and these sort of more complex analytic things.
Okay.
It's sort of a big industry moving between these things and stuff. Yeah, good question. It's so hard. I realize I use this language and I don't even think about it. Okay, so these two elliptic curves like this, yeah, this is the exercise. So these two things are equivalent if and only if there is some matrix, A, B, C, D, living in SL2Z, such that tau is equal to A tau prime plus B divided by C tau prime plus D. And you might remember back to your complex analysis class and recognize this as like the Möbius transformation on the upper half plane associated to this guy. I did say in the abstract there would be like a tiny amount of complex analysis in this talk. Okay, so why do I say all this? Well, it's because a modular form is going to be some sort of function on the moduli space of complex elliptic curves. And we want to, so it's going to take a complex elliptic curve and spit out a complex number. That's what you think about it as. The definition is slightly different. So now I can define what a modular form is. A modular form is a holomorphic function, something now from an f from the upper half plane to C, such that, and I'm going to ask for two conditions to hold. The first one is that if we change our tau by one of these elements in SL2Z, we apply this Möbius transformation to tau, we would like our function to be invariant under that transformation, because we would like our function to be invariant with respect to equivalences of elliptic curves. So we're going to say something like this, plus b divided by c tau plus d. I want this to be equal to f of tau. And this is for all, again, these a, b, c, d's in SL2Z. Okay, I'll get back to this condition in a second. You, with experience, will see the big gap here. And think about that if you're taking notes too. The second point is I want to have a little bit control as h travels up. So in other words, as z travels to infinity, I want to ask that this function does not go crazy. I want to ask for some sort of analyticity or complex analyticity. And the proper way to say this is to note, or to notice that f tau plus 1 is equal to f of tau. That just comes from this equation up here. So this guy is periodic. And now we can rewrite this function as follows. We have f, which is a function from the upper half plane to C. We have this map, which goes from the upper half plane to the open annulus. The open unit annulus in the complex numbers. So of course this is like the open unit disk with the 0 point removed. What is this guy here? Well, this is this classic thing from complex analysis, which sends something in the upper half plane to e2 pi I tau. Yeah. So this is this nice thing here. And because this function is periodic like this, it means that there is going to be another function here, which I'll call f tilde, which makes this diagram commute. So in other words, we can factor this, modular form from H to C into something that goes from this open disk to C. So this happens for free. This is not a condition yet. The condition in part 2 is that I would like f tilde to be holomorphic at 0. So infinity here is sent to 0 here. And so asking for holomorphicity at infinity here is asking for holomorphicity at 0 here. Hence this condition.
So what you call infinity is that infinity.
Yeah, I infinity. Maybe that's not a great name for it. Yep, exactly.
What is sent to 1, so the other two?
What is sent to 1 here? That will be the real line.
Ah, so it's, okay.
Yeah. Such that f prime is holomorphic at q equals 0. So I'll be reasonably consistent, and that's because it's consistent in the literature, with using tau for my guys living in the upper half plane, and q for my things living in this open disk. So tau living here and q living there. Are there any other questions on this point? Okay. So someone should mention that I haven't finished this definition, but maybe you're just being kind to me. So what happens is, if you run through this definition, it turns out to be not a silly definition, but a kind of redundant definition. Because basic complex analysis will tell you, okay, now I have some sort of bounded periodic function, holomorphic function, on some little patch of the complex plane. And so actually, all modular forms using this definition are constant. So it's not a great definition. So what we need to do is we need to loosen it up a little bit. We need to add a little bit of flexibility, which will give us more objects to play with. Of course, I'll give you some examples in a second, because at the moment there's only one ones. And the way to do this is, well, there's two ways to do this. The first one, and this is not something everyone has to do, but it's something I have to do, is change holomorphic to meromorphic. Like I said, this is not strictly necessary. And I'm going to add some sort of weight here. So this function f is not necessarily going to be totally invariant with respect to this SL2 action on the upper half plane, but it's going to be somehow like weighted invariant. We're going to ask for some sort of factor of this SL2Z action to pop out in some controllable way. So, and the thing thing we ask for is we ask for this denominator here to pop out with a factor of k. And this k is going to be called the weight of this modular form. So k is the weight of okay. So it's taken me 2 boards now and some good questions, which I don't always have good answers to give you some strange definition. So I want to give you some examples now. We'll try to illustrate why these things are interesting to study.
So it's really that you want to cross out that one, that one,
Was it like this? Yeah, you're right. So I want holomorphic here, and I want to be a little more flexible here. I hope all of you taking notes have a rubber on the other side of your pencil. Okay. Okay, good catch. Okay, so let me give you some examples now. Because I don't really know what mathematics is without examples. Okay, so the first example actually comes in a family of examples, and these are called Eisenstein series. And they're defined as follows for each integer, let's say natural number k. And for sort of convergence reasons, we're going to ask for this number to be greater than or equal to 2. We define the following function on the upper half plane. I'm going to call it e to k. It's going to be the 2k Eisenstein series. And it's defined by sending some tau in the upper half plane to the following sum. n inside integers, take away origin. 1 divided by m plus tau n. Okay?
There's no k yet.
You guys are really paying attention. So, I piqued your interest so soon. Very nice. I'm sure some of you can tell me exactly where I didn't finish the definition too. Okay, so this is what the weight 2k Eisenstein series looks like. And you can maybe roughly see why I need k to be greater than or equal to 2, because I need some sort of convergence or absolute convergence on this sum here. And that's not going to happen if I take k to be 1, for example.
Well, if k is equal to 2, then you have conditional convergence.
I've got a 2k here, so it
Oh,
should be.
yeah, yes, indeed.
Oh.
Yeah, but you do have an Eisenstein series of 2, but you don't call it here.
Yeah, there is. Yeah, you probably know more about the technicalities than me. I just sort of rule it out. Okay, thank you. Okay, so this is what the modular form looks like of weight 2k. But I introduced this notation here with this f prime, this f tilde for a reason, and that's because these f tildes are what are called Q expansions. And why are they called Q expansions? Well, because I asked them to be holomorphic or meromorphic at Q equals 0. So in particular, I have some sort of Taylor or Laurent series expansion. And it's the coefficients of these Q expansions that are very interesting. So in this case, we end up with a formula like this. E 2k minus 3k plus the sum. Okay, where Q again is an element in this open annulus. Well, not necessarily annulus now, but open disk, which looks like this.
So this is an example for the F, satisfying those.
Yeah, so this is an example of the F, and this is the F prime, where I've plugged in this tau goes to this Q thing here. Yeah, sorry, so this first formula is really for an F, like the input is really the tau. And then the second formula, the input is a tau, which I then send to the open annulus like this. And then I
Isn't the second one
oh, sorry.
Isn't the second one the normalized Eisenstein series? I think that there should be a zeta factor.
I thought I copied it correctly. This is the, zeta factor here. It's popping Like, I mean, the
If the coefficients shouldn't be rational.
I mean, the coefficients, this first one is not, but there are,
But that's a Bernoulli number. Bernoulli numbers are rational.
yeah, this will, but this would just be a rational thing, it wouldn't necessarily be an integer.
Yes, but that means you should have the one you write down there is the normalized Eisenstein series, so there you divide by number of the
Okay.
factor up there. So they differ by constants. So maybe
Okay.
that's not too much of an issue, but
I'm going to use some notation. I thought I copied it correctly, but it's very easy to know. I'm going to use some notation from spectral sequences, where the upper dot means that this is equivalent up to a unit. And a unit in the complex numbers is obviously a bit of a mistake, but you find that unit.
Fudge factor is a good name.
Oh, that's a good one too. Makes it seem a bit lighter. But okay, so I have to define what a lot of these things here are. So for example, these guys here are the Bernoulli numbers. And these guys here are what are called the generalized divisor functions, which you can write like this. So this is a sigma k minus 1 evaluated at n. This is the sum of all the positive divisors of n, and you take the sum to the k minus 1 of all of these guys. And so the point of these Q expansions is that the coefficients of these Q expansions are interesting. They're interesting number theoretical objects, up to a u. Okay?
This is not yet the F tilde, right?
This is a formula for the F tilde. The Q is now you can think of as a guy living in the angles. Okay, so this is a nice example, or at least I think it's a nice example. But another nice one is called the discriminant. Okay, and it can be given by this formula, unless things differ by a unit again. I blame Wikipedia because I checked this recently. It's like someone made a mistake. I think so. I should write to the CEO of Wikipedia. There are textbooks for these reasons too. So one cool thing about modular forms is that you can add and subtract them, you can multiply them, and since I asked for this guy just to be meromorphic, you can actually divide them as well. So I can define a discriminant modular form just by using this formula. And there's just constants times Eisenstein series to some power, and a linear combination with other constants times Eisenstein series to some power. And this spits out another modular form which has a nice name delta. And the reason why it has a nice name delta is because its Q expansion is very nice. So this time I'm only going to give you the Q expansion. I'm not going to write down the regular formula, but it's general practice to always put a tau here rather than a Q. just to be in
Historical reason.
Okay. Where these taus are called, what? This is not a definition. This is the definition. So these tau functions here are some functions that were studied by Ramanujan, and one of the amazing things is that if you assemble them into the coefficients of Q expansion of modular form, you can check that it's a modular form.
I don't think you mean this.
This?
I think you want the variable on the left-hand side to be a key.
Oh, sure. This seems very sloppy, but I'm of course always taking Q to be e2 pi I tau. So there's that's that's right. Well, yes, you're very right. Yeah, but I couldn't talk about it. I couldn't talk about something. Yes. So it's Ramanujan's fault for this. Okay, so this tau is a different tau. Thanks for mentioning it. And this is another thing that is interesting in number theory. It's something that was come up with originally by Ramanujan, and so happens to be expressible in a modular form like this. Okay?
This is some variation of this Eisenstein series. Are they completely different examples, or is this all like in some class of?
So it turns out that everything can be expressed as sort of products and sums and division by Eisenstein series, but it's very hard to keep track of what happens to this Q expansion. Some other things can happen. But yeah, actually I'll write that down now. So here are some facts. The first fact is, as a ring, so I mentioned that you can multiply and divide and add and subtract modular forms, so they form a ring. That's what we expect, and the constants exist there, so you have 1 and 0. So as a ring, this ring of modular forms is actually not super exciting. It's generated by the 4th Eisenstein series, the 6th Eisenstein series, and the inverse of this delta, inverse of this discrete. So as a ring, it's a reasonably simple ring to study, but it's, and the star here means that I'm considering all weights at once. Okay, so as a ring, these things are not super exciting, but if you fix a particular weight, you say I want to look at things with weight 24, as you often do, there are some remarkable properties. So each, so for each fixed weight, so MFK, this has a finite dimensional subspace of holomorphic modular forms. So a holomorphic modular form is just where I remember, I keep the word holomorphic here instead of crossing it out. And this should be rather amazing because if you think about these modular forms in terms of power series and their Q expansion, there are just lots of power series, and they don't necessarily have to have, the coefficients of these power series don't necessarily have to have anything to do with each other. And so the fact that putting a restriction on these power series, like asking them to satisfy this transformation property and stuff like this, puts so many restrictions on it that it turns out that for each fixed weight, you only have a finite dimensional amount of such modular forms. So this puts lots of restrictions on it. For example, if you know that in one weight you only have 2 dimensions of freedom, then you only need to check Q expansions up to the 2nd degree before you know how these vectors in this 2-dimensional vector space behave with respect to each other. Another way to phrase it is, for example, in weight 8, there are 2 different modular forms that pop up. There is the weight 8 Eisenstein series, and there's also the weight 4 Eisenstein series multiplied with the weight 4 Eisenstein series. So these are 2 modular forms that live in degree 8, but it turns out that the dimension of weight 8 holomorphic modular forms is 1. So these things must differ only by a unit, and in fact that unit turns out to be 1. And that tells you lots of things now about the coefficients of these modular forms. One of them is going to have coefficients given like this, and the other one is going to have coefficients given by when you take the product of 2 power series. So that's where the strength of modular forms comes in, is this finite dimensionality.
So, are they just polynomials in E4 and E6 without the delta inverse?
Exactly. That's exactly the holomorphic guys. The delta inverse is really, now we're looking at nonmorphic guys. Exactly. Okay. I'm very scared of this marker.
Wait. I mean, E8 is not whole.
Yeah, and it also tells you something nice about the Bernoulli numbers and about these guys too.
No, but this dimension series is so easy, but you just have to look at the combinations. For 4 and 6?
Yeah, and it just turns out it happens to be E4 squared. Okay, so there's another way to study these modular forms and really hone in on the Q expansions, and that's to use Hecke operators. I don't need a title, I just need a definition. Okay, so now I can define what the Hecke operators are. For each n greater than or equal to 1, we define some operators like this, the nth Hecke operator, which goes from, it's just a linear transformation from the weight k modular forms to the weight k modular forms. K and n don't have anything to do with each other. And you define this map as follows. If you have a modular form of weight k, then you send it to the following thing. You send it to the function which sends tau to the following sum. Okay. I'll write it down and then I'll say something, or else I'll get lost. Okay, so you send it to the following formula. I want you to look at this formula in these instances. In particular, I don't want you to worry about this n to the k minus 1. You can just move that away. That's not super important. What's important here is that you're looking at all the lattices all sublattices of your fixed lattice. Remember, tau gives us a lattice by these pictures over here. And we're looking at all sublattices of our fixed lattice, given by tau, which have rank, what's it called? Index, n. Which have index n inside our original lattice. And then we're taking the sum over all these guys, all these sublattices, and we're applying f to that. So what we're doing is we're sort of looking at all the sublattices of a given lattice, or all certain subgroups of a certain complex elliptic curve, and we're applying our modular form to this, and we're sort of taking an average, sort of like a weighted average. That's where the n to the minus 1 comes from. And the k just has something to do with the weight. Okay? So this is something seemingly random that you can do, but just like everything in the literature of modular forms, it seems to have just amazing properties. So maybe I'll write them here. Here's some facts about these Hecke operators.
F of lambda, because the invariance is with the weight. So what's the meaning of F of lambda?
So here, I was being a little bit lazy. You could think about these modular forms as really being defined on some set of lattices satisfying a slightly different equivalence relation. So it can be defined as a modular form f is a function from the set of lattices to C, such that f of C lambda is equal to C to the k f of lambda, where C is some complex unit now. But then I find it hard to express this holomorphicity because I put some complex structure on the set of lattices, which is essentially what I'm doing with this sort of parameterization. Well, me, what someone on Wikipedia. Okay, so here are some facts about these Hecke operators. A lot of these you can just check by hand using this formula. I don't claim that it's easy, but I claim that it's in every single modular form textbook in the world. So there's lots of good references for this. So if you apply the nth Hecke operator to an Eisenstein series, what you end up with is an eigenvector. So the Eisenstein series, eigenvectors for the nth Hecke operator, and the eigenvalue, well, that is the interesting part. This is the nth coefficient in the Q expansion of E2K. So in other words, these Hecke operators kind of hone in on what your Q expansions are. Often the eigenvalues and the eigenvectors, well, the eigenvalues of these Hecke operators have something to do with the Q expansion of the eigenvectors. So that's one fact. The second fact is that if you apply this to delta, the exact same thing happens. You end up with an eigenvector whose eigenvalue is the nth entry in the Q expansion for this discriminant guy. Okay? So not every modular form is eigenvector. Don't even think that even makes sense with linear algebra. But there is an amazing fact, and this was proved by Hecke, and is I think the reason why Hecke operator is named after him, is that MFK, so for each fixed weight k, or you can consider all k at once, this complex vector space has a basis of simultaneous eigenforms, so eigenvectors, eigenforms, same thing, eigenforms for all n. Well, let's say for all Tn. So there is some basis for MFK, which is not only, where each element in this basis is not only an eigenvector for Tn, but for every Tn, which is pretty amazing. I mean, there's got an infinite amount of operators here. And the proof of this is just a little bit of the spectral theorem, or just spectral theorem. It's just not a super intense application. Okay? And using this sort of idea, with the idea that the Hecke operators really tell you something about the Q expansion, you can do something that Mordell did, which is answer a question of Ramanujan, which is Mordell showed that the coefficients of this tau function satisfy some sort of multiplicativity if m and n coprime. So using these Hecke operators and the fact that they really hone in on the Q expansion, you can actually prove arithmetic properties of modular forms and the coefficients of their Q expansions using these sorts of operators. And the proof here, I encourage you to try to find. I think, not to be a broken record, it's even on the Wikipedia page for Hecke operators.
Are there other proofs?
Of this? Well, the original proof by Mordell didn't quite use that language, but no, all the proofs look like the proof with Hecke operators. Ramanujan conjectured this because it felt it to be true. But no, I mean, of course there probably are other proofs, but the only proofs I've seen use these operators. Okay. Any other
These
questions?
operators themselves have some kind of multiplicative property.
Yeah, exactly. So they have some sort of property when you compose them together, you get some sort of sum over different divisors of the m and the n that you feed in, and something like this. It's a very nice one. And that essentially gives you this. That's exactly how it works. Okay. So that was roughly the first half of what I wanted to say, and thankfully that was also roughly the half of the time that I have. Oh no, a little bit more. Okay. So what I want to say now, I'll write down in words. So a modular form is, it looks like a weird sentence so far. So it is a function, as I defined for UF, from the half plane to C with a modularity condition. Let's ignore the meromorphic holomorphic things for now. And this was kind of mentioned briefly when I answered the question of Marius, you can also reinterpret these not necessarily as functions on the upper half plane, but on the set of lattices, satisfying some sort of weight condition. So this is a function f prime, say g, on the set of lattices in C to C with, and again, it's going to have some sort of modularity condition. Okay? But, I mean, you're defining something on the set of lattices, and each lattice gives you an elliptic curve. And I'm asking you, and you know that two elliptic curves are the same if their lattices differ by a unit, and I'm telling you that these G's don't necessarily respect this difference by a unit, but they respect it up to some sort of modularity condition. They respect it up to this weight here. So in other words, a modular form is actually a function on the moduli of elliptic curves, which, and I'll put in quotes here, twists with respect to equivalence classes of elliptic curves. Okay, so I'm just sort of like slowly reworking this definition, of course, without proving it. And the final thing I want to write down here is that sort of mid-20th century algebraic geometry gives us a very concrete way to express things like this. In other words, a function on the moduli of elliptic curves with a twist with respect to equivalence classes of these elliptic curves can be viewed as a global section of a sheaf, which I'll just write as omega to the tensor k, on the moduli of elliptic curves over C. The nice thing about this final reinterpretation is that it's clear where the complex numbers come in. It's, at least if you know the definitions of these things, it's clear that you can just cross out this word here and we still have a valid definition. So in other words, if we use this definition, this lower definition, and replace the complex numbers with any other ring R, then we have a definition for modular forms over general rings.
Your omega is what I think it is.
I hope so. Yeah, it's some sort of dual line. Yeah.
I think it's a line bundle.
Exactly. Yeah. It should be the line bundle of differentials or coordinates. Right? Yeah. Okay. So I'm going to do a few things on this board, which step pretty far. So please ask questions. Not that I feel like I've restrained you, but please continue. That's the last thing.
You explain the derived now? Or?
Oh, you're excited for it. Okay, so yes, so what we can do now is we can just take this last definition as a definition for integral modular forms. So definition, take this line bundle, whatever it is, take its global sections over some moduli of elliptic curves, and this is going to be the integral modular forms. I haven't told you how to compute them or if they have any nice properties, but this is all sort of work of Deline and Rappaport and Serre and Katz and lots of people in the 50s, 60s, and 70s and 80s. And I'm going to give you a theorem, actually no, an observation followed by a theorem. So I haven't told you what this line bundle is, but it is a line bundle. So it's some sort of bundle. When you think of a line bundle or some sort of sheaf on a space, you think about something like smooth functions on this space or something like this. But in particular, the global sections or any of the sections of this sort of bundle, they should be abelian groups. So this thing is a sheaf of abelian groups. And in particular, we can now form a very silly ring. If we have a bunch of abelian groups, well, I'll just write a formula. So if we consider all the k at once, like a big sum of them, so when k is positive, we're taking tensor powers of this thing, and when k is negative, we take joules, and we take tensor powers of that. This is a ring, or rather, it is a sheaf of rings. And again, this is for a very silly reason, because if you have a section in here, like if you have some f inside omega to the k, and you have some g inside omega to the l, then you have some g tensor, some f tensor g inside omega to the k plus l.
I don't find that obvious at all. I mean, I get infinite sums.
Yes, then we should restrict to like homogeneous things. So we should really take, yeah, this should be considered as a graded ring. Yeah, that's a good point. Yeah. So we shouldn't have one element we shouldn't consider in potentially all degrees. We should look at each degree. Okay? So now I'm going to state a theorem, which is one of the most exciting theorems in homotopy theory, if I can spell anyone's name. I've written it 1,000 times, but you know, if I could type it immediately, but it's the spelling that's hard. Okay, so there's a theorem of three homotopy theorists called Ghost, Hopkins, and Miller, and it says the following. It says that there is a sheaf of derived rings, which I'll just call big O. It's supposed to look like some sort of derived structure sheaf, such that, well, I'll write down the such that in a second, because I would like to just say what a derived ring is. I don't want to lose you guys on a technicality. So I'll give you a definition over here. A derived ring, this is, and depending on what you mean by derived ring, this either is a definition or it's just close to. So a derived ring is a space R with homotopy coherent addition and multiplication. So I won't say, I'll say just heuristically what I mean by homotopy coherent addition and multiplication. I mean you have a set, you have a space. So that's a set with a topology. And I ask that it has an addition and a multiplication, which is continuous with respect to this topology. But I don't ask that multiplication and addition follow the usual rules of a ring up to equality. I want to ask that they only hold up to homotopy. So in other words, if I have 2 points in this space, well, let's say 3 points in this space, and I want to multiply x and y followed by z, or y with z followed by x, I'm not going to say that these two different points are equal. I'm just going to say that there's a path between them in this space. They're sort of homotopic. And homotopy coherent means that I'm not just asking for one homotopy between different associators when I multiply 3 different elements, but I'm asking for higher homotopies when I multiply 4, 5, 6, n many elements, and all these homotopies work well together. And yeah, there's some sort of magical theory in the background here, which again, I'm sure a lot of other people here would be very happy to explain to you, me included. But in particular, it's space. So in particular, a space has homotopy groups. So the homotopy classes are maps from a sphere into that space. So what's amazing about this sheaf of derived rings, O, is that when you take its homotopy groups, it spits out, why do they use pi? It spits out this sheaf of integral modular forms. No, I want to just say as sheaves. Yep. Okay. Any other questions?
Sheaf on what?
A sheaf on the tile side on the modular stack here.
What about the yacht?
They vanish. Yeah. So it's a nice, when you look at it just as a sheaf, it's a very nicely behaved thing. It's sort of, on odd homotopy groups it vanishes, on even homotopy groups it gives you these line bundles. You think everything's going very nicely.
From what you've been saying, it's not clear at all that the left-hand side lives over this M of yours.
The same.
Yeah, I mean, it should be sheaf on M, right?
Yeah, so what you can do is you've got O, which is a legitimate sheaf of derived rings there. And then you can section-wise take homotopy groups and consider that as a pre-sheaf, and then sheafify, and you'll get this guy here. And then that sheafification is the same as this sheaf here, both as now sheaves of abelian groups on this modular stack M.
But now the modular stack comes in your explanation
Uh-huh.
at the end, but not for the left-hand side.
It's always a sheaf.
Yes, sorry, you're right. I haven't said that. So this is a sheaf of derived rings on M. Of course.
That's what I was
That's what
asking
you wanted. Yeah.
to do.
You were trying to lead me there, and I was going everywhere else. Okay, cool. Thank you. Okay, so there's actually a whole bunch of other nice properties of this derived ring. In fact, if you know a little bit about derived rings, you can actually construct something like this fairly easily using like algorithm plane construction or something like this. What's cool is that this has lots of nice homotopy properties, and this O actually gives you what's called a sheaf of elliptic cohomology theories, which again, I want to talk about, but this is not a lecture series, it's just a lecture.
Is this only for non-negative?
So actually, these derived rings should be considered sort of as non-connectivity infinity rings, so they should have negative homotopy groups, and then this also holds in the negative.
Are you saying that in any line bundle you can make this type of construction happen, or
Absolutely not. This is a very specific thing.
for any graded algebra, or even more specific?
No, it's a very, very specific thing. Yeah, it's kind of amazing that this happens at all. Yeah, it's kind of an industry trying to generalize this result. Okay, so I'll make a quick definition now. So TMF is what we call the global sections of this thing. So this is now a sheaf of derived rings. I can take it, and the homotopy groups of this sheaf of derived rings look like the homotopy groups of my integral modular forms. So the global sections of my derived guy are probably also some type of nice modular forms. So we call that TMF, also known as topological modular forms. The derived ring of topological modular forms. Okay. If you talk to me or Leonard or more and more Sven, you'll hear us talking about this all the time. Anything else? Okay, so now I can finally get to the statement of my. Oh, I didn't realize you were doing that the whole time.
Yeah.
Now I can get to the titular objects of this talk, these derived Hecke operators. And spoiler alert, the result is not going to be very. The result that I write up is not going to be very surprising. Basically, we have some sort of derived version of modular forms, and there exists some sort of derived version of Hecke operators. I'm scared of my cup, and it's full of chalk. Okay. So this is one of the constructions from my thesis. Is there are maps, so that look like this. They're maps. They're sort of maps between derived rings, but they're not maps of derived rings. In the same way you can have a map between rings as just a map of the building groups. So there are maps like this between derived rings. Such that, and I could go on all day about some nice properties that these things hold, that hold for these things, but I would rather just like to say that they behave well with respect to the Hecke operators that hopefully are just here. Right. So such that if you take the homotopy groups of this guy, the two case homotopy groups of TMF, you apply Tn, two case homotopy groups of TMF, then there's maps like this that go to the ring of modular forms now of weight k. So these are sort of comparison maps, and you have the Hecke's Hecke operators here, which I'll write as Hecke operators, which you should only write and not read out loud. And I say that this diagram can use, such that this diagram can use. So in other words, if you have some guys here that you know their image in this ring of modular forms, then you can probably compute what these derived Hecke operators are on these elements in this homotopy group by first sending them down to the regular world of modular forms and then applying this map here. Of course, that's if you want to do calculations here. But actually, the fact that this commutative diagram exists already tells you a lot of information about the downstairs world of algebra. Because this map here, going downstairs, this is neither injective nor surjective. So in particular, the fact that it's not surjective means that if you have a modular form here that's not in the image of this map, then, if you have a modular form here that is in the image of this map, then its image under the algebraic Hecke operator has to also be in the image of this map. And we know everything about the image of this map. So that gives you restrictions on modular forms.
And what happened to the 1 over n?
It should still be there. And the 1 over n, I'm not sure if to regard it as a technicality or as a feature. It's just that it should be there. Okay. Yes. Okay, so now I just want to play a very quick game with you. And it's a game that I've shown to a few homotopy theorists, and I don't know if they're all super impressed, but but I'd like to show it to you because it's pretty, it's fun and it's a little novel. So there is an element inside this group here. There's an element here. So this is the 30th stable homotopy group of spheres. So what you can do is you can look at homotopy groups of spheres, so that is just pi n of Sm, and then thankfully, Mr. Freudenthal has proved that if you suspend this in both variables, you start looking at pi n plus k of Sm plus k. As k gets higher and higher, this process stabilizes, and you end up with these stable homotopy groups. So what you can do is you can use a computer and try to calculate these homotopy groups. It's really very hard. In fact, a computer probably doesn't do it. And you can check that this is some element in the stable homotopy groups of spheres. Why is this interesting? Why does that have anything to do with this? Well, it's because the following two facts. These maps Tn are S-linear, as S is the initial derived ring. So just like all maps of abelian groups, if you have a map of abelian groups F, then f of x plus x, or f of 2x, is the same as 2f of x, because it's a map of abelian groups. In other words, it's z-linear. It's linear with respect to the initial ring. In the same sense, in the derived world, you have the same thing. So now I have a map of derived rings, so it's going to be linear with respect to the sphere, or linear with respect to this stable sphere. So this is one fact. The other fact is that because this is the initial derived ring, there is a unit map, and this sends this element beta cubed into pi 30 of TMF, which turns out to be Z mod 30. You don't need a computer necessarily to do this, but lots of measures. And help from other people. Okay, so here's some random facts that I'm giving you, and now I want to show you the random trick that I think is pretty neat. So on the one hand, you can try to compute what this is. This is an endomorphism of TMF, so it induces an endomorphism of its homotopy groups. This beta is an element in pi 30, and I'm just applying this endomorphism to it. And I want to know what kind of element it spits out in this group here. There are only 3 options, so hopefully you can figure out which one. But I can use this top fact that these Tn are linear with respect to the sphere to just pull out this beta. I mean, it's the same as pulling out an n if you have a map of abelian groups, or a C if you have a map of complex vector spaces. Get a beta cubed, Tn of 1, and now I say, I know that 1 is a weight 0 modular form here, and it's sent to something here, and I know how to apply Hecke operators to my weight 0 modular forms. And it turns out that this is beta cubed times sigma 1 of n divided by n. So let me summarize again. This first equality is by sphere linearity, and the second equality is classical. In other words, it holds for the classical Hecke operators. Okay? So we did that calculation. Very nice. And we should be proud of ourselves. And when I first did it, I was like, phew, okay, let's do something else Lennart wants me to do. But then I realized that there's more than one way to calculate this. And this is another fact that is just totally random, but it's very useful in this situation. There's just an equality of elements inside pi 30 of T. And again, you have to know something about this topological modular forms. You have to know something about the cohomology groups of this sheaf that I started with and some spectral sequence to get this, but you can do this calculation. It's available in the literature. So this is now Tn of alpha squared delta, where this alpha is now some mystery element inside pi 3 of T. Okay? Who cares about this equality? It exists. We can reference things in math. We can't learn everything. But we can now play the exact same tricks. We have an alpha. It's in these homotopy groups here, and in fact, it comes from the sphere. So using linearity, we pull out alpha. We get this. And I already told you what this is. We already know how to apply the Hecke operators to this discriminant form. We end up with these Roman tau functions. Okay? And now I see the same equality again. I see alpha squared times delta, which is equal to beta cubed. So I get tau n times beta cubed. So I have two different ways now to calculate these two things, and I have two different coefficients that pop up in front of my beta. I know this is not very conclusive ending when I do it just in the corner, but let me do that. So in other words, we have shown that tau n is equal to sigma 1n divided by n inside this group. So we've only done it inside this group, the z mod 3z. So this is not an equality of integers, it's just an equality modulo 3. Okay? And you might look at this and be like, okay, cool, I learned these things today. Someone says they behave like this today, cool, whatever. But this is a nice classical equality due to Roman. And there are a bunch of similar equalities, congruences you can come up with using the fact that TMF is a derived ring, that these Tn's are linear with respect to the sphere, and just some calculations. You end up with a whole bunch of weird congruences between modular forms, and then you try to figure out what you should do from there. Anyway, that's all.